session 1, which is the Stats 101. We will have 3 speakers. Thank you, Anjali, Runjhun, and Sneha, for giving us your time and volunteering as a speaker. Thank you so much for being here for us. And just one last last week one. We do provide certificate of participation, and the eligibility would be something like you have to attend at least 3 of the 4 sessions, and there will be a quiz after all the 4 sessions. So at the end of the session, there is going to be a quiz, and you have to score at least 50% of it. Like score 50% or more, and you'll have a certificate of participation. And just a reminder, our second session is going to be about data distribution, and it will be on Saturday, April 30 at 11 a.m. EDT and 8:30 p.m. IST. Thank you for bearing with me. Thank you so much to the speakers, attendees, and sponsors. Note that all the recording will be available in a few weeks, and the link will be available in the Slack later on. Thank you so much. And over to you, Sneha. Let me stop this screen share.
Thank you, Shaistha. Bear with me 1 minute, everybody, as I share my screen. All right. Okay, so thank you everyone for joining us today. We are very, very excited about this webinar series. Personally, I'm very passionate about statistics within the machine learning area. So I'm really excited for kicking off this session. I just want to, okay, there we go. Yeah, just want to quickly go over some of the things that we're gonna talk about in this session. And if you've noticed, this is a 4-part series. We're trying to break it down into 4 broad level topics. Just want to set expectations here that although we're going to hit all the foundational concepts, go into technicalities of what those concepts mean, I think what we are really aiming for in this series is to also have like the application piece down, and we want to help everybody build an intuition for these concepts around statistics, so that if there's anybody out there who feels statistics is difficult or boring or doesn't come easily, we want to, and we hope that after this series, you won't feel that way anymore about statistics. So with that, let's get into what this session will cover. We're just going to introduce what is statistics. I'm sure most of you know that already, but just that's going to be our starting point. We're going to talk a little bit about why it is important to have an understanding and intuition about statistics with respect to machine learning. And then we're going to go into conceptual understanding around the 2 key areas of statistics, which is descriptive and inferential statistics. And we're going to kind of close it out with emphasizing a little bit about population and sampling, because that definitely holds like a good amount of relevance for machine learning. With that, let's get right into it. All right, so statistics essentially is a part of mathematics, which provides us some tools and methods to really handle, work with, and understand the data. There are 2 broad applications of statistics. One is to describe the data, which leads to the descriptive statistics part. And the other is to infer from data, which is what forms the inferential statistics part. And 2 of our other speakers today are going to take you through like more details around these, and they will highlight some intuition and concepts around descriptive and inferential statistics. Okay, so statistics and machine learning are, in my opinion, quite closely coupled. We hear today a lot of talk around new machine learning algorithms, advanced techniques, and whatnot. And there are so many packages and so many tools of really implementing those. And a lot of people, I think, do it without an understanding of what's happening under the hood. More critically, outside the fancy space of just implementing or building and deploying machine learning models or algorithms, I think it's really important to understand why you're choosing that model, how it's handling your data, and how you're interpreting the results of it. Because when you start applying these techniques within a real world space, I think it becomes more and more relevant to have that understanding so that you're able to make those decisions in an informed way, and you can reduce the errors or some misses that you may have with respect to what you could have prevented in terms of implementing a wrong model, or maybe you didn't handle or account for certain outliers or things like that. Moving on, I'm just going to talk a little bit about why machine learning needs statistics, or why it's a good idea for all of us here to understand it a little bit better. I think how I like to think about it is through 5 key areas of machine learning that utilize the understanding of statistics. And with that, like, you don't have to be an expert. You don't have to go into complex mathematical formulae or start deriving things or get like into the weeds of it. And that's literally what our goal is here through the webinar series, like I mentioned. But just to have an understanding around why you need to have a feel or intuition for statistics as you go through these different areas of machine learning. So we all begin with just looking at data. Exploratory data analysis obviously forms like the first step in coming up with the right business problem, the right business question that you're going to handle with the help of machine learning. And data preparation really benefits from statistical methods, which is where you begin to understand what the different distribution of your variables are, and do you have missing values, do you have any outliers, and how you should handle those if you should. It also kind of leads into the next step, where after you've looked at distributions, after you've kind of identified which features should go into your model, which should not, which again involves statistics by means of identifying relationship between variables. The next piece of around model evaluation is really where I think between these 2 steps, there is a portion where you look at your data and you split it into test and train and how you're going to sample them. So sampling, again, is another statistical concept that helps us do this in a scientifically accurate way. And then coming to model evaluation, understanding what are the different algorithms available to you, running those, understanding the parameters that come out of it in your output are all related to understanding of some statistical concepts. Third piece is model selection. When you look at the different model output parameters that come out and you're making inferences or interpreting the results and understanding which model is doing better, which model is explaining the variability in my data better. I think all of those concepts, again, are deeply rooted in statistics. And we'll talk about some of those, I think, in the later stages where we talk about p-values, we talk about hypothesis testing and things like that, which hopefully will help you understand those model outputs a little bit better. The next piece is model presentation. So you've built the school model, you've selected the best one, and what are you now, like, you have to go and convince somebody that, okay, this is the one that I think that works best to answer this business case, and here's why I want to use it. So you need to make another person who is maybe not even aware of the machine learning techniques as well, and you got to condense it, summarize it, and share it in a way that's intuitive and understandable, which is where statistics again comes to the rescue in terms of sharing that information in a more descriptive way. Lastly, we come to prediction. And when you're running predictions with machine learning, you need to understand how to interpret the expected variability in your predictions and kind of understand what all that means when you're running those prediction algorithms. With that, I would like to hand it over to Anjali, who's going to, oh, oops, sorry. Before that, I almost missed this. Okay, I want to talk a little bit more about the different types of data that we have, and then Anjali will take us through the descriptive statistics portion of this talk. So as most of you might be aware, or you must have heard, we have different types of data, or different data types. We have numerical data, categorical. I think those are two broad categories which are quite popular, and you come across them often enough. What we want to highlight here are the 4 levels of measurement, which kind of tie to those data types. Nominal, ordinal, interval, and ratio are the 4 ones that we are categorizing here. And you'll see in the next piece, for example, how or what these mean. Wait, okay, so this guy right here, if you look to all the way to the right at ratio, that's the one that's kind of the closest interaction with your numerical variables, right? Where you're calculating ratios and you're kind of working with your numerical variables. As you move from there to the left and all the way over nominal, I think it gets more categorical. I won't go into much detail into this, but I will pause after this for questions if anybody has those. Nominal and ordinal are almost got everything to do with categorical variables, and I'll just point out the difference between the two. Nominal, like this example says, eye color, for example, could be 4 different types, right? It could be black, blue, brown, something else. So those don't have any relevance of order in them, but they're just labels or buckets. So those are the categorical variables that have just those buckets built into them without any relevance of order. The next one, which is ordinal, as the name suggests, is indicative of having the relevance of order built into it. For example, you have customer surveys, or here it talks about level of satisfaction, where you're saying maybe 1, 2, 3, 4, or something like that. And although those are labels and buckets, they also have the relevance of order built into them. Like 1 could mean more and 4 could mean less, or the other way around. All right, so I'll pause real quick here for questions. Okay, so with that, I'll pass it over to Anjali, who's going to talk through descriptive statistics in detail. Take it away, Anjali.
Thank you, Sneha. Okay, I'll just share my screen. All right. So we're talking about descriptive statistics here. So first, as Sneha discussed, the definition of statistics, which is literally just the process of collecting data, organizing data, and then summarizing it and presenting it to the audience so that they can understand what data is. So statistics is essentially divided into very 2 basic parts, which is descriptive and inferential. So if we talk about the descriptive statistics, which is what I'm going to talking about, which is what I'm going to take you through. So it's just when we're collecting data and then we're organizing it and summarizing data using numbers and graphs. So when you have a data set, it's a very raw data set. You have just numbers and you don't understand what those numbers mean. You don't really know what this indicates. If I just put a raw data set in front of you, it doesn't really indicate anything. But if I just practice descriptive statistics, then you'd understand that that data actually indicates something. So descriptive statistics is the practice of organizing and summarizing data using numbers and graphs. So we use graphs to summarize the data, and we use different modes of central tendency we use measures of variability and other methods which we use to describe data in a way which is easier for the audience to understand. What's the second part of statistics doing? That's inferential statistics. That's basically analyzing the data for us. When I've given you the data information, when I've given you what the data indicates, then there is inferential statistics which comes into picture, which helps us analyze the data and draw necessary conclusions from it that, yeah, this data represents this. Okay, so I'll just take you through some examples which will help you understand better. These are the examples of graph, which helps us show that, yeah, this data has this percentage of this thing represented and other percentage of some other thing represented. So data helps us understand the data. Graphs helps us understand the data better in a visual manner. Now, there's the example. Suppose you have in a city a population of 100,000 people, and we can't just calculate the whole the data. If we are calculating the inferential and differential statistics modes, we are calculating different mean, medians, and modes for different sample data. Then I would just want to clarify two technical terms which I'm gonna be using more. So one is sample data, which represents the part of the population which you have surveyed and you are analyzing. So you can't just go around and talk to 100,000 people in a city and ask them what their preferences are about a subject. You take a sample of people and you ask them what they like, and then you draw conclusions about the whole population using the sample population that you have surveyed, right? So sample data is the amount of the part of population which you are surveying, and data points is the individual data which you have in a raw data set. So data points and sample data is something I'm going to be using throughout the slides. So I just wanted to clear this up. So we have a population of 100,000 people, and I'm going out and I'm surveying 100 people out of those 100,000 people, because I want to know what is the total number of people who have jobs in the tech sector, right? So we have a sample size of 100. The number of people we are surveying is 100. So we have a sample size of 100. And let us suppose that 34 out of 100 have jobs in tech. Now we're not going out to survey a group of people which belong to, a particular job sector, because then we'll have a very skewed kind of estimate for what we're trying to measure. We are just surveying random people. So one key while surveying people is we survey random people. We don't survey a group of people. We survey very random people. So we are surveying random people, and we found out that 34 people out of 100 have jobs in tech, which leads us to the conclusion that the average of people who have jobs in tech is 0.34. So 0.34 is the average, which is the measure of descriptive statistics. But then what is inferential statistics? I am drawing the conclusion about the whole 100,000 people in the city using this average, which is 0.34, and I'm saying that 34% of the people have job in tech sector in the city. In the whole, out of whole 100,000 people, there are 34,000 people, 34% of people who have jobs in the tech sector. So I'm drawing the inference, the conclusion about the whole city by using just 100 people, the 100 people I've measured. Now, this thing I've highlighted is increasing the sample size gives more accurate results, obviously. If you're surveying more people, then obviously you have more accuracy. Suppose you have estimated 100 people, out of which 58 work in tech and 42 do not. So you have 0.58 as the average. But if you are going out and surveying 1,000 people, then you get something like 587 people who are working in tech and 413 people who are not. So 587 divided by 1,000 would give you 58.7, which is a more accurate result. So increasing the sample size, which will give you more accurate results. Now, there's a second example, of course, you all vote, right? So before the voting results are announced, you see on news channels, media channels, they're having their exit polls and stuff. What does that actually represent? So how do they do it? Why one media channel claims that they have better and more precise results than the other media channels? Because they have gone around and surveyed more number of people. So they have more accuracy in their results. And that's how they measure the, suppose in a country, there's a voting, suppose in that same city, there's a voting, 100,000 people. And I go out and survey 100 people. And another one of my friends, she goes out and surveys 1,000 people, right? So I have a less accuracy and she has a more accuracy in her results. Why? Because she's interviewing more people and she's surveying more large amount of people. So she has a more, she has a large sample data, which gives her more precise results. That's how they claim that we have more precise results, because they have surveyed a large number of people, and that's how they get the predict the results before the actual voting results are announced. So this is another example of how we describe data through a raw data set, and how we actually conclude the basic results, which we can conclude through the data sets. Now, we have central tendency, which is a mode of descriptive statistics. What is central tendency? I have a very basic definition here. So central tendency is a descriptive summary of a data set through a single value that represents the center of the data distribution. What does it mean? I have a data distribution, right? So the middlemost number, the centermost number, it's very self-explanatory from central tendency itself, that what it represents. It represents the centermost data point of the data distribution, right? We have a data distribution. If we have the centermost number, then we know that this is the number which will define the whole data set. We need a number which defines the whole data distribution. If I'm talking about this data set, and if I'm saying that, yeah, this is the mode of central tendency, this number, then I know that this number is representing that data. Now, there are two questions which you're going to get the answers to. And these are the most important questions when we're talking about data, which is, what single number best represents our data? Now, you all know that we have three modes of central tendency, right? We have mean, we have median, and we have mode. I've written it right here. So we have three modes of central tendency. So what mode of central tendency best represents the data? Because mean would give you another data point, median would give you a different data point, and mode will give you a different data point. What number do you think best represents that data? That depends on the data itself, right? We'll just discuss it in the coming slides. And the second point is, are the scores or the data points? Now you have a data, you have different data points in a data. So what do you think? What are the scores, the data points packed together or spread out? How packed together is, what is the difference between the data points is what we're going to talk about in variability. So before I go ahead and discuss the mean, median, mode, I want to discuss about the central tendency examples. Suppose, okay, out of 100 marks, suppose you've gotten 94 in a test in class, right? Now you don't know that if that score is a good score, a bad score. You don't know that because you don't know the average. You don't know the class's whole average, how much other students have scored, because how you have scored is always relative, right? If someone has scored better than you, then your score is not the best, right? So if I tell you that, okay, I've calculated, I've seen the, the whole class's marks distribution, and I know I've calculated the average of that distribution, and I know that the average is 80. Right? And you have scored 94. So you have scored more than what half of the class has scored, right? Half of the class has the score 80 because we're literally going to the center. We're calculating the central tendency. That means we're going to the center of the data. And you have scored more than half of the people. That means you have scored, you have a good score, right? So that's one example which helps you clarify more about central tendency. Now let's just, I'll just discuss briefly about how we calculate mean, median, mode before going further, because I saw some people asking about the, the basics of it. So, okay. Are there any doubts up till now? Okay. So mean, median, and mode. We know that mean is, suppose we have a data set. We have 10 data points in our data set. And we have the scores. We have 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. How do we calculate the mean? We add all those things and we divide it by the number of data points. We take the average. So mean is just the sum divided by the total data points. How do we calculate the median? For median, you have to arrange your data in an increasing or a decreasing order. And if your data has a data points, has even number of data points, then you take the middlemost number and the one which comes after the middlemost number, and you have to add both of them and divide it by 2. And mode is the and if the in the median also if the data points are odd number of data points, then you just divide the data points, number of data points, by 2, and then you go to the number which n by 2th number, and that would be a median in the increased or decreased series. Mode is the most number of times a number has occurred in a data set. Suppose a number is occurring very frequently. Suppose if I have a data set 1, 2, 2, 2, 3. So 2 is occurring 3 times. That means 2 is the mode. So I hope this is clear. And there's an example here. So this will help you clear out which mode of distribution you should use with what data set. Because now I've told you about 3 data sets, right? Mean, median, and mode. Now you have got a data set and you don't know which one to use. How do you know which one to use? Is median the best representing my data? Is mode the best representing my data? Or is mean best representing my data? I have no clue. So let's just look at the data set. Let's just calculate its mean and median. Okay, you guys can just try it out yourself. Calculate the mean and median of this data set and just drop the answers in the comment section if you can. I'll just wait for 5 seconds and then I'll continue. Okay, so we have got this data set, right? 70, 72, 74, 76, 80, and 114, right? Now the solutions are something like this. We have mean 81 and median 75. It's very self-explanatory from the values itself that which is the better mode of representation in this case. We have got mean, which is 81, which lies between 80 and 114. And we've got median 75, which is literally the half, like it lies in the center. So we know that the mode of central tendency, which helps us reach the center of the data, it's the median which is best representing this data. Why is it so? Why mean is giving us this skewed value, and why median is the correct mode of representation here? It's because these values, 70, 72, 74, 76, 80, these are very close values, but we have got this outlier here. The number which is very different from a data set, which just doesn't stand out, which just stands out in a data set. We know that these values are very close, but this value right here is, it's an outlier. It's, how should I call it? It's very, it has a very large difference from the numbers which are actually here. Now we actually use the measures of central tendency to represent the data. For example, the example I talked to you earlier about, that if I have got 94 marks and the class average is 80, then I know that I've done a good job, right? But in this case, suppose these are the marks of students in a class and I'm saying I've got 76, right? And someone says that the mean is 81. That means my marks are not that good because I've gotten less than half of the marks, half of what the class has got, right? Because 81 is representing the center for us. That's what we have been taught, that 81 is the center, but that's not a very correct representation because I have scored good. I have scored 76, which is better than what half of the class has scored. But still, my average is giving me a very skewed prediction about my data, which is not right. But here median, if I say median is 75, so the average is 75 and I'm getting 76, that means my marks are good enough. And I have scored better than half of what half of the class has scored, right? So median is the better representation. And what caused this mean to be a skewed mean in this case is the golfer who scored 114 is an outlier because there is a number which is not sitting well with the rest of the data points. So the median best describes the scores of the team because the mean is higher than almost all of the scores in the data set. Okay, so if we go to the next, these are a lot of points. It's the characteristics of mean. So this will help, I'll just discuss the highlighted part because I think I'm taking too much of time. So mean is used as a mode only when the data is scaled and not highly skewed. That is, if the data is balanced, just like Sneha talked about the interval and ratio data, which is equally spaced. So mean is used as a mode when there are no outliers. We have a balanced graph. So like this, we have a normal distribution where this peak is representing the mean and the graph is symmetrical on both the sides, which means there are no outliers present in this data set, the data set which this graph is representing, right? The next graph is this one, negative skew and positive skew. If the graph is right aligned, then the graph is known as negatively skewed graph. Then while when the graph is right aligned, it is known as positively skewed graph, okay? So the mean is supposed to be on the peak, right? It's supposed to be on the peak, but it's right aligned. Why? Because we have got an outlier in a place. We have got an outlier which has skewed our mean. And in this case also, we have got an outlier which has skewed our mean to the right. So if we want a mean, if we want to calculate a mean with a data set, so we need to have outliers on both the sides. If we have got an outlier which is greater than the rest of the data points, then we need to have an outlier which is less than the rest of the data points, right? Next is this normal distribution. Just like I talked about this curve, which is rightly skewed, negative skewed and positive skewed. This is something which is known as kurtosis. So kurtosis is when the graph is having low outliers and high number of outliers. This red graph has got a very tailed peak, which represents a large number of outliers present in the data set. While this one, the blue one, it represents a very less number of outliers, which is also not favorable. The one which is favorable is the black one, which has got just the right amount of outliers. Next is the characteristics of median, where median is used as a mode of central tendency only when the data is interval level but highly skewed. The data is equally spaced only, but it's very highly skewed. That means it has a large number of outliers. It has a large number of data points in it which does not belong there, right? It is a very skewed data distribution set. Now, when is mode represent? When mode is the best representation? Mode is used when a particular score dominates over the distribution. Suppose there's a class and I ask, what flavor of ice cream do you like? And there are 60 people in a class and 20 of them, they just say that, yeah, we like the mint flavored the most. So I am getting a data set where a particular score dominates over the distribution. I'm getting 20 for mint, 2 for chocolates, 3 for strawberries, and so on, right? So the mint one is dominating. The mode is 20 because the score of mint ice cream flavored people is more than the other. So it's dominating. That's when we use mode as a representation for central tendency, when we know that a particular score is dominating over the distribution, right? This is the bimodal situation. So what happens is, suppose you have the same class where 20 people are saying that they prefer the mint flavor and rest of the 20 people are saying that they prefer the chocolate flavored ice cream. So there are 2 peaks now in the graph. There are 2 kinds of domination on the whole data distribution, which is, so this is the bimodal curve where we have 2 particularly dominating data points, right? Next is variability. So variability indicates the data points, which how data points are spread out. We have a data set, right? And we have got data points in that data set. How those data points are spread out, how is the difference between them? Now, would you like the data set to be variable, highly variable, or less variable? So I have a very general question, which is, why do we even evaluate data? Why do we even get data? Why do we even go out and conduct surveys? So that we can predict a trend from that particular data. We can predict that, yeah, if that's the data, that's how the trend is going, then in the future, this is how it's going to happen. This is how things are going to happen, right? But the data is not predictable in case of variable data. If it's a highly variable data, then it's very unsteady, it's very unstable, and it's unpredictable. If the data set is unpredictable, then it's of no use to people, data scientists, because it's highly variable. So greater the variability, it means less the consistency, and it's a very less accurate the measure of central tendency, right? So how do we measure the variability between standard deviation? How do we measure the variability in a data set? We do it through central standard deviation and variance. So that's what we're going to see next. But before that, there's an example. So we have this first data set, we have the second data set, and this third data set, right? So they all have mean 6. All these 3 data sets have a mean 6 only. So this data set and this data set, can you predict the next number in this data set and this data set? I'm sure it's very easy because 8, 7, 6, 5, 4, you know, the next data point is 3 only. And in this, I'm sure you have already predicted it's 6, right? In this data set, however, can you predict? No, you can't, because it's highly variable. It's a variable data and you cannot predict what's going to happen next, right? Because we don't see any similarities. And the difference between the variables is very irregular and unsteady. So these are the example of where high consistency is preferable and high variability is not. So how do we measure high variability and how do we prevent it? Okay, before that, we have these very complicated formulas of variance and standard deviation. I'm sure many of you have, you know, doubts about it because it looks very complicated, but it's not. So do we have time? Can we discuss this?
Yeah. So, hey, Anjali, sorry for disturbing. There
Yeah.
are quite a few questions about mean. I mean, people are asking, why do we need mean in the first place if we can use median? And there were some people asking about why use outliers itself. So could you please answer that?
Why use outliers?
I mean, why look into outliers when you can just leave it out?
No, okay. So suppose we have a data set and we are getting the surveys. We can't just leave one observation out. You see, we have an outlier as a part of the data point, and all the data points are a part of that data distribution. It's there, right? We need to have that to calculate the whole data. Otherwise, the data is skewed. Because we are we're just doing something which is preferable for us. We're just leaving out the part which is unpreferable. That's not how it works. We need to take into account everything. We need to keep everything in mind. If the trend is going down in one of the year, then we need to know why did that happen? Because it can okay, I'll just give an example. Suppose we are calculating the trends for each year. We have calculated for 2013, for 2014, 15, 16, 17, and 18. And now I want to devise a strategy as a data scientist to, just for a particular thing, to sell a particular product. Now for 13, 14, 15, 16, and 17, we have this, an increased curve in the selling of this particular product. And we know that we did these things right. But in this case, we have a graph which is going down, and we know that we did something wrong. We need to identify what we did wrong, right? So we need to know what outliers, it's compulsory to just include everything there so that the data or our predictions are not skewed and we don't do anything wrong. The outliers are supposed to be there because they are a part of our surveyed calculations, or should I say data points. We can't just leave something out just because that would be more comfortable for us. Okay. What was the other question, Shaistha?
Yeah, there's another question that someone, Jian, is asking that, can you give more examples of how mode is used for data analysis? Like what cases mode is needed for analysis?
Mode, okay. So when suppose there's a data distribution, I have a large amount of data, and I have seen this trend where a lot of people, out of 60 people, suppose 40 people are preferring the same thing, then I would obviously go with the majority because majority of people are preferring the same thing. So what the majority is following, I will follow too. So that's what mode is. When there is a particular data which is dominating over the whole data distribution, then mode is used. When like mean, okay. So in mean, we're using it when there are when there are no excessive use of outliers, right? We are using median when there are excessive use of outliers so that we can get accurate measurements, because it's very minimum susceptibility to outliers. It's very least affected by the outliers present. In the mode, when you see in a data distribution that a number is occurring a lot of times, like it's the dominant data point in the distribution, it's the number which is the majority is preferring, then we use mode. We use mode as a data distribution. We represent that, yes, 20 number of people are liking this thing, so we're gonna go with the majority, because at the end of the day, you have to work with the majority, right? What's the other question?
Yeah, there's another question that why do we need mean at all? Because when data is normally distributed, mean is equal to median and is also similar to the mode. In that case, in this case, can we use just Can we just use median instead?
Okay. In the case where the data is normally distributed, where mean, median, and mode are equal, you can use whatever you want. Okay. I'm not saying if there are outliers are not present, then you can't use mean. Obviously, you can use mean, because in that case, you're gonna get the same thing in all the distribution. You can't use mode because there is a data which is not dominating, but you can obviously use median. It will give you the same result. It's not it's just that the mean is sometimes easy to evaluate in large data sets, because you just have to calculate the sum, which you can do using the programming. Right now it will seem a little difficult, because obviously you have to do it manually, but there are programming stuff which we have made which can make the sum easier. So mean is easier to calculate, that's why we use mean, but you can use median too. It's not a necessity. Are there any more questions?
That's it for the questions now. That's it.
Okay.
Thank you.
Shaistha, can we discuss the formulas? Do we have time left?
Yeah, we can go over it quickly if we can.
Okay. So, we have a data set. And suppose we have 4 data points in my data set. We calculate the mean of that data set. Now, I have individually subtracted the mean from the data points and squared that number. Suppose I have 1, 2, 3, 4. I calculate the mean of 1 plus 2 plus 3 plus 4, which is 4, 7, 9, 10. 10 divided by 4, which is 2.5, right? And I 1 minus 2.5 and whole squared of that quantity. Then 2 minus 2.5 whole squared of that quantity. Just like that, we continue with the rest of the data points, and then divided by the total data points. And and that's how we calculate the variance, which is sigma square. And standard deviation is the square root of the variance, which is sigma only. This looks very scary, but it's just the sum. It's literally just the sum. When you're calculating 1 minus the mean, and then 2 minus mean, 3 minus mean whole square, and then 4 minus mean whole square, then just add those data, and then just divide it by the total number of data points. That's how you get population. And now you'd be wondering why I've done n minus 1 here when I've taken sample, because it's just graphically prove that it gives us more accurate results. You can play with the numbers and Excel and stuff, and you'll know that this gives us more accurate results when we're working with sample data, which is something which is the part of population data. So we're mostly using this sample data stuff. So we're using a number which is 1 less than the data points. Okay. Next is variance and standard deviation characteristics, some of the characteristics, and why variance is not something which we use to define the variability, and standard deviation is something which we use more often. Is why? Because variance is the squared quantity of the difference, which is a very unrealistically large number. And it's unpreferable. And standard deviation is in the same scale as mean. So it's not the squared quantity of any number. It's just when you are square rooting the variance, then you're just coming back to the quantity which you have calculated from. It's in the same scale. It's not a squared quantity of anything. Also, okay, now the conclusions which we have derived. Now you have a standard deviation. You have a number which represents the standard deviation of a data distribution. How would you define that this data is variable and this data is consistent? If you have a small standard deviation, then that data is less variable and more preferable. And that data is easy to predict. If you have a large standard deviation, that data is inconsistent and its data points have a large difference between them. We can represent it through the graph. See, this is a normal distribution data. This is a data which has a very small standard deviation. And the green one is the data with the very large standard deviation, right? We can just get to correlation. So you have 2 quantities, 2 variables. So what correlation is an entirely new concept, which we use to understand the relationship between the variables, right? So I'll just give you a short example and I'll explain you using the graphs only. So we'll discuss the correlation coefficient here. So we just look at this graph, only this graph for now. We have this graph. Suppose this horizontal axis represents Okay, let's take an example. Suppose this horizontal axis represents the duration of a movie. 50 minutes, 60 minutes, 70, 80, 90. And this represents the ratings the movie has got. 2 stars, 3 stars, 4 stars, 5 stars, right? And the graph is going upward. That means the slope is positive. What does that represent? That represents that as the movie's durations is increasing, as the movie's duration is larger, the ratings are also increasing. As the x-axis, the quantity in the x-axis is increasing, the quantity in the y-axis is also increasing. The longer the duration of the movie, the higher the ratings. So the graph is increasing. And this is also an increasing graph, and this is a constant graph. This is a decreasing graph. As the duration of the movie is increasing, as the duration of the movie is increasing, the rating is decreasing, right? So what does it represent? It represents the correlation between the two variables, that is the duration of the movie and the ratings which it has got, right? So this line, it has the points which are scattered very closely to the line. And this line has points which are scattered very far away. And this is just a constant graph. It represents that there is no correlation. That the correlation is just that the thing is very constant. So we'll just discuss about these two, where the graph has points which are very closely scattered and very farly scattered. So it represents the direction of trend. The correlation coefficient discusses the direction of trend. If the duration of movie if the longer the duration of the movie, the higher the ratings, or the shorter the duration of the movie, the higher the ratings. It discusses the trends. So if the trend is negative, is in the negative direction, then the coefficient, the correlation coefficient is negative. And if the direction of trend is in the upward direction, then the correlation coefficient is positive, right? And it also tells us about the magnitude of the correlation coefficient. If the points are scattered very close to the line, then the correlation coefficient is very high. But at the same time, if the points are scattered very far away, then the correlation coefficient is very low, right? It's the constant correlation coefficient. Now, there is one thing which is very important in correlation coefficient, which is, I just told you guys that the longer duration movies have gotten higher ratings in this case, right? Okay. So it does not mean that correlation is not causation, which means the longer duration movies have got higher rating. It doesn't mean that longer duration movies are the reason why the movies are getting the higher rating. It could be something to do with the genre. It could be that the shorter duration movies are documentaries, which are generally boring and not preferable by the wider audience. It could be anything, but correlation is not cause and effect. It's not that if the duration, if we are seeing a trend in the graph that the duration is longer, that means the ratings are high. If we're seeing that in a graph, that does not mean that making a longer duration movie would get you higher ratings. It does not mean that. So I think that's where I end, and I think Runjhun can take over now. Thank you so much, guys. And if you guys have any questions, Shaistha.
Yeah, Anjali, there's one question that someone is asking, please explain interval and ratio in the level of measurements once more, because they kind of found it.
In what, sorry?
Interval and ratio in the level of measurements, like give up some sample measurements, maybe numbers for them to understand.
I don't get which topic they're talking about, sample intervals.
I think it's... Yeah, I think it's about the correlation one.
Okay. I'll just clear it up. Okay, so in the correlation coefficient questions, it's basically when the correlation coefficient, okay, it lies between -1 and 1, okay? So when the correlation coefficient is between -1 and 0, then the slope is going down. That means as the quantity on the x direction is increasing, the quantity on the y direction is decreasing. It's a negative slope. And when the correlation coefficient is between 0 and 1, that means that as the quantity on the x direction is increasing, the quantity on the y direction is also increasing, right? Now, if in between 0 to 1, if the correlation coefficient is closer to 1, that represents that the points will be scattered too close to the line, the slope. And if the correlation coefficient is less, then the points are scattered too far away from the line. That's what it represents. That's it. So Shaistha, any more questions?
Thanks. There's another question in the chat. This is the last question, and we'll move on for the next speaker. The last question is, how is correlation or causation connected to variance and SDT?
How is correlation and causation? Oh, it's not. Okay,
connected to variance and SDT.
Okay. So it's connected to regression and stuff, which goes beyond the scope of the lecture, and it just helps us understand the relationship between the variables more. So if we're talking about a particular situation where we have two things which relate to each other, then we just want to clear that up, that correlation is not always causation, right? That's the main agenda of this sliders. Of why I am discussing correlation is because I wanted to clear that up, that correlation is not causation. So correlation is not cause and effect. If you think that a movie's duration has something to do with the the ratings, then it's wrong. The movie it has other factors which are affecting why the trend is happening. If you it's not representative of the data itself. If you have got a data and if you just create a correlation graph, then it does not predict the data in the further causes, right? It's not correlation. Correlation is not the cause and effect situation. That's all. It does not represent the data. It's just establishing the current relationship between the two variables. It's not predictable, so it's not related to the descriptive statistics part. Yeah. Is that all?
Yeah. So. Yes. So Anjali, sorry everyone. We are kind of running low on time. So Anjali will answer other questions. There's one more question in the chat page, and we're going to just pass on the baton to Runjhun. Okay.
Okay. So should I just okay? You can take over, Runjhun.
All right. Thank you, Anjali. You can move on to the next slide. Okay, so I hope you guys are still with us. I know we are ahead of time and I won't take much of your time. So let's talk about inferential statistics. That's the other type of stats that we know. So Anjali talked about like descriptive statistic, what it is. And so just giving a one-liner definition, it would be summarizing the characteristics of a data set. We got to know about the mean, what kind of data it is, it's skewed or not, what's the most frequent number that's coming in our data. So that's the characteristics of the data set, right? But now we need to do something with it because we need to draw some conclusion out of it. So we will be using inferential statistics, which helps us to come to conclusions and make predictions based on our data. So it has two main uses. Firstly, it helps in making estimates of a population. So how do we make an estimation? It's a whole lot of process, and I won't be going deep into it because so inferential statistics is a lot. It's a big topic in stats, and we do have 2 sessions purely dedicated to it. So I'm just scratching the tip of the iceberg right now. So for example, if I say how many people like using Instagram in US, so I know you can't just go to every person and talk, okay, you like Instagram or not. You will be making an estimation. So for suppose 60% of people in US like Instagram. So this is an estimation about whole population. And secondly, the second use of inferential stats is testing the hypothesis to draw a conclusion about population. So you will ask, what's an hypothesis? So hypothesis is something, an assumption statement, I would say. It's not something that it's true. It can be, it might not be. So how it gets to conclusion, when we back it up with some data. So if I say, for example, relationship between Instagram users and age of the users. So we have, if I say, okay, from the age group of 20 to 30, people are spending more time on Instagram. So you can say, okay, in this age group, people are using Instagram more. So that means they like Instagram more. So that's some hypothesis. But if we use these characteristics that Anjali defined in descriptive stats, if we use these characteristics and back it up with our concrete values, this hypothesis will be reaching the conclusion part. So this is what inferential statistics is all about. I hope I made this clear. So I talked about a very important term here. It's populations. What is it, and why it is so important that we're talking a lot about population? Anjali, can you go to next slide? All right. So population, as the name suggests, we all know, population includes all the elements from the data set, right? So it's the whole lot of data. If I say, just take a survey in your country, and you need to ask each and every person what's the favorite color of their car. So this is a lot of work. You can't do it. Anybody would be refused to, ask each and every person, because the population would be in millions or billions, and it is technically not possible, but we do need the data. So what do we do? Next slide, please. So we do sampling. So this is the solution that we come up with. If we have a lot of data, we have a good amount of population that we have to survey or we have to analyze, use sampling. So sampling is the process selecting the selecting the sample from the population. Sample is basically a subset of from the whole lot of population. Now, taking the same example, if I say, just discard your whole population and go to your street or your city and ask everybody, or like 10 houses, or in your neighborhood, 4 houses, just ask what's the favorite color of the car. So this is something like, doable. You can ask them and you can collect the data. So this is how sampling, this is what sampling is, because you take that dimension thing out of it, and you just take a very small part of your data and ask that question, what you were asking the whole population. Let's talk about how sampling works. Next slide. All right, so how does sampling work? So now if I ask you, how many people like blue cars? So taking inspiration from Anjali's example, we say the population is 100,000 or 1 lakh. And I just say you can take a subset of 100 people. So assuming that 20 people like blue cars, and this is a simple thing that, okay, 20 people like out of 100 people like blue cars. So it means 20% of the samples like blue cars, right? So next slide. But we need to keep in mind the margin of error, because we are just estimating. That's what inferential statistics do, right? So we are just assuming that, okay, 20 people, like from 100 people, 10 people out of 100, like blue cars. So this has a margin of error. If I say plus minus 2%, so our estimation would be 20% of the whole sample plus minus 2%. That's the error. So this is like in my estimation, but I don't think it's it's very reliable. So let's just get on with a bigger sample. Next slide. So this is our next sample. It's double. It's 10 times the earlier data. Now it's 1,000. So what do we see here? We have, assuming we have 220 people liking blue cars, right? So now our estimation changes. We have 22% of the people of the sample liking blue cars, because I'm not taking the whole population. I have to say 22% of the sample, right? Next slide. Now this margin of error decreases because I have considered a good amount of people in ratio with the population. So this is a good measure. So this is a good, accurate answer, accurate estimation. I would say that this is, it has lesser margin and it is quite accurate because our earlier data was very vague. So this is how we, sample this data, but this is like a very, in a layman term that I'm describing it, we have so many methods that we use. We can't just, say 1% or 2% is the error rate, or we have this confidence level of 95%. We can't say it like that. We have many methods to define it, and we will be discussing it in upcoming sessions. Because this is just Stats 101, I wanted to, keep it light because inferential stats a lot to talk about in first session. Next slide. All right, so ending up with the difference. So as Anjali said, descriptive statistics is all about information and characteristics. So we talk about mean, we talk about mode, we talk about median, we talk about is the data, centered correctly, like what's the distribution of it. And we, on the other hand, we talk about inferential statistics. So it is more about inferring something, right? The definition of the word also tells us that we are inferring something from this data set. So we are inferencing some conclusion, some prediction about the population. All right, so next point would be it helps in organizing, sorry, it helps in organizing, analyzing, and present the data in the meaningful manner. And so how we are organizing it by taking in account of outliers, we're taking in account of missing values as well, and we are talking about what's the average. So we are analyzing it in a better way. And then if we have a good data set, if I manage my data in a good manner, I can make a good hypothesis. I can make a good assumption statement so that, I have a good estimation, all right, these many percentage of votes I will be getting for some party. So that's what Anjali talked about when she was talking about voting system. On the other hand, inferential statistics, it helps in comparing data. Why comparing? Because we are comparing two features. For say, because just as I said, like age of the user and how many hours spent on it on Instagram. So so we are making a comparison of this, right? How many hours, what's the age? So if you are like around 40 or you're in your 50s, you are possibly you're taking less time on Instagram. So that's how we compare it. We make the hypothesis, as I said, we do predictions. And as I'm repeating this thing, that hypothesis is a lot, it's like a very broad topic, and we make predictions out of it. And lastly, the last point is descriptive stats is all about bar charts, bar graph, pie charts, because we have to analyze it and we have to make our data presentable and describe it as you say in descriptive statistics. And on the other hand, we have inferential. It's all about probability. So this is the formula for probability function that we use generally because we are estimating the things. We are not sure about it, but we are getting close enough to the reality. So this is what all about inferential and descriptive. That is it from my side. I hope I didn't take too much of time.
Yeah.
If you have any questions, all our panelists are open to questions.
Yeah, there is one question.
Go ahead.
Yeah, there's one question that how do you get your margin of error? How do you get your margin of error? That's one of the questions.
All right. So can you go back, Anjali, a bit? Yeah. So, all right. So margin of error is something that is calculated by, keeping in mind of outliers and the mean and average, because, as Anjali told us that if your data is right skewed or something like that, if we had an outlier of 114 that was in this data, so that's an error. That's a marginal error because we do have people who might not like, blue cars. That's what. So this is like a nominative category. But if you have something like continuous value, we can just flow into that margin of error. Okay, I am sure that 1% of people would be like, my estimation could be 23% or might be 21%. That's my estimation. That's the margin of error that I keep. So this is calculated by keeping in mind the descriptive characteristics that we have. And we will be talking more about it, definitely, when we are talking about data distribution in the next session. So let's keep it for next session. And any questions? Thank you for asking this.
No, that's it, I guess. Thanks so much, Sneha, Anjali, and Runjhun. You did a great job. And thank you so much for volunteering for us and taking up your time and doing such great talks. Just a reminder to the participants that we do provide participation of certification of participation. That is, you have to fit in at least 2 criteria. That is, you have to attend at least 3 out of the 4 first 4 sessions and obtain at least 50% marks for the final quizzes. And just to make it clear that the recordings will be made available in like a couple of weeks, and all the link to the slide and both to the recording will be made available on the Slack. If you have more questions and if you want to go, if you want to discuss more about it, you're welcome to have a conversation on Slack. Please do post your questions on Slack and we'll be happy to like answer them. And thank you so much for joining us today, and see you on April 30, Saturday at 11 a.m. EDT or 8:30 p.m. IST for the second session on data distribution. Thank you so much. Have a nice day. Bye.